In this video, we are going to look at problem number 8 in section 14.7. Okay. And this problem is asking you to compute a triple integral of the function x over the region R in three-dimensional space, where R is the region that is below the plane. It's below the plane z is equal to 4, but above the paraboloid, z is equal to x squared plus y squared. Okay? So we're looking at this solid region in here inside of this paraboloid. Okay, I've got plots here over in Mathematica. You can see that I've plotted the paraboloid, the plane. I've done a 3D region plot of that region, and that's the region here. And what we're seeing also is that we've got a density function, rho of x comma y comma z is equal to x. So what I've shown in this problem is I've shown that if you were to slice this surface, okay, this region, and if you were to take the x is equal to 1 slice of it, you would get x is equal to 1, y and z would just be equal to 1. So I have plotted the density function if I were to slice this thing at x is equal to 1, and it would create this parabola. And the density everywhere, the volume density, is a constant. That's why it's the same color. I then plotted this also for another slice, x is equal to 1, negative 1, and you can see that the density, again, is the same number. It's constant everywhere. The colors here are not the same color. This is a constant negative 1. This is a constant 1. Okay. The code that I use to generate for this problem is the following. I will let you pause this video at this point to get all this code typed in so you can see what's going on. The first thing I want to talk about is this plot here. I'm plotting the paraboloid in parametric form. The reason I'm plotting it in parametric form is because this problem, section 14.7, they ask us to do this problem in cylindrical coordinates. So we need to do this problem in cylindrical coordinates, which means that we need to transform our x, y, and z problem, and we need to transform it over to the coordinates r, theta, and z. Alright, so we need to use the transform t, r, theta, and z. And we know that x is r cosine theta, y is r sine theta, and z is just z. Okay. So we're going to kind of break this problem into steps. Here is the code that I use to generate these plots. And then we want to try to set the mass of this region integral up into cylindrical coordinates. And that's what we will work on now. Okay. So what we need to do is we need to take this integral and evaluate it, and we need to transform to cylindrical. There's a couple parts to this problem. We need to take the density function, which is a function of x, y, and z, and it's x in this case, and we need to turn that over into rho, r, theta, and z variables, and that just is a simple substitution according to the cylindrical coordinates transformation. Our region is x, our variables are x, y, and z. X is given as r cosine theta. So if I want to change variables, I would let x is equal to r cosine theta, y is equal to r sine theta, and z is just equal to z. and our density function in terms of the variables r, theta, and z is simply r cosine theta. So we now have the r cosine theta. Okay? We've converted our density function over. But we want to then do this as a dz, dr, d theta integral. Okay? And so these are our new variables. We are changing from x, y, and z. dv in this case could have been maybe like dz, dx, dy, if that was the ordering you wanted to try. That becomes the new variables dz, dr, d theta. Because we have changed variables, we always need a compensation term. That would be the determinant of the Jacobian of this transformation. So if you were to compute the determinant of the Jacobian of this transformation, you would simply get r. Okay. The tricky part is figuring out what the limits need to be. Z needs to go from somewhere to somewhere. Theta needs to go from somewhere to somewhere. And, oops, sorry, R, I'm sorry, I got the wrong order, R from somewhere to somewhere, and theta goes from somewhere to somewhere. So the trick here is, this is where all the work, this is where you got to do the work. Okay, this part was pretty easy to compute. So what we need to do is we know that we're going from this cylinder, this paraboloid up to that plane. So what we need to do is we need to describe parametrically, describe in terms of r's and thetas. We need to describe in terms of r and theta the cylinder z is equal to x squared plus y squared. Right? So if you're going to describe this parametrically, it's going to be a surface. There's two variables. The things that change in this problem is the radius as you move around this circle, and then at different levels we have different radii of our circles. So the radius and the theta variable are all that is changing. So if you want to figure out what this looks like in cylindrical coordinates, you would just plug in the transform. X is equal to r cosine theta. And you would square it, and you would add that to r sine of theta squared. And that simplifies to r squared. Okay? So the parametric description of that, or the cylindrical coordinates description of that cylinder is z is equal to r squared. What does that mean to us? That means that if you had a function, describe that parametrically as r and theta, the x variable was r cosine theta, that can't change. Y is equal to r sine theta. And we have just shown that z is equal to r squared. And you now have a function in 3D, but it has only two variables. And that is the ideal candidate for a parametric plot 3D, which is exactly what I did here in this code. I did a parametric plot 3D, r cosine theta, r sine theta, r squared, and then, okay, we need to figure out what the r's and thetas go from. Okay, you can play around with that and experiment it if you wanted, but I think the way that you know what r and theta go from is, take a look here. We want this paraboloid to be topped out at z is equal to 4. So when z is equal to 4, that's r squared, 4 is equal to r squared, that says that r is going to go from, say, -2 to 2. And then theta, you want to go around the whole paraboloid, right? They didn't say half of it. They didn't cut this thing in half. They did not do that. They said the whole thing. So that means theta would go from 0 to 2 pi. And that's exactly what I did in the Mathematica code. I plotted r from 0 to 2 and theta from 0 to 2 pi. And that is how you get this purple region right here. That is, I didn't plot that as x squared plus y squared equals z. I did not do this as a plot 3D. I did this as a parametric plot. Okay? So, what this helps us do is this helps us figure out, instead of z is equal to x squared plus y squared, this is z is equal to r squared. And then z goes up to 4. Okay. And so this will help us figure out the first limit of our integral. This is going to go from z is equal to r squared up to z is equal to 4. Again, you're allowed to have functions as your limits in these triple integrals. It just so happens that the function is now a function of the cylindrical coordinates r, theta, and z. Okay, so let's pick back up the r cosine theta, the r term, and then we've done the dz, and now we need dr and d theta. And I think we've established that r goes from 0 to 2 here, because theta is going to go from 0 to 2 pi. So r will go from 0 to 2, and theta will go from 0 to 2 pi. So here is the integral that you need to compute. This is the cylindrical coordinates integral. Okay. And this is the cylindrical coordinates version of x dz dy dx, for example. So if you were to try to describe this, the original problem in terms of Cartesian coordinates, you would have had to go from z is equal to x squared plus y squared up to 4. Z is equal to 4. And then once you got to z is equal to 4 in the z equal 4 plane, you would have had a region in the xy plane that would have looked like a circle of radius 2. So then you would have had to do this as your 2D region. And then that would have been, for example, say maybe y is equal to negative square root 4 minus x squared, y up to the square root of 4 plus x squared, and then x would have gone from, say, negative 2 to 2. Okay. So these two integrals, whichever one you feel like working, they should give the same answer. They will give the same number, but they are just in different coordinate systems. They're in different coordinates. This is in XYZ coordinates, and this is in R, theta, Z cylindrical coordinates. But they should give the same answer. Okay? And let's take a look at that now. I've shown you the different plots. Okay, keeping in mind that the densities are constant in the YZ plane. And so I computed these two integrals in Mathematica, the density function. I think you can see I defined the density function here, okay, in this code. So let me give you another look at that. If you need to pause this video again, you can be typing in this code. I've defined my density function, and then I've done a density plot when x is equal to 1 and x is equal to negative 1. Clearly we can change slices in the x direction if we want, or you can plot different slices if you choose. But the point being that when I typed both of these integrals in, okay, let me show you side by side. So I typed this integral in Cartesian coordinates, I typed the other integral in polar coordinates, and they both come out to be 0. They both come out to be the same number. Okay? The reason it's 0 is that we must have the same on one side of this, since the density is x. When x becomes negative, the density is a negative density, and then on this side it's a positive density, and the two in a sense cancel each other out and leave a mass of 0. The point, what you should see, is that these answers should always come out to be the same. Okay, so I think I've shown how to write the paraboloid in terms of cylindrical coordinates. I've shown how to transform the mass integrals over into cylindrical coordinates. And you know, this problem is kind of fun. You could play around with it by changing the density function, for example, plus y cubed times z. Make a legitimate function of 3 variables. And maybe you could take different slices of this. You could take the x equal 2 slice of this and say the x equal -3 slice. And you could rerun this program. And you know, this could be a very challenging integral to compute. The Mathematica should chomp on it quite nicely, though. Here's your paraboloid. Here's the density functions. Right? It looks like since it's changing in x, y, and z, it's a little lighter on this side, heavier on this side, lighter on this side in the second slice. Now these are not the same numbers. Since they're blue, they're not the same numbers. This may not be a density of -1 and -1 or something, but these are just relative numbers. And okay, it looks like in this problem that we still got a 0 density. So maybe let's make this x. I'm just trying to show you a problem where you don't get 0. Let's see if this did it. Nope. I don't know. Z squared. Let's put a minus somewhere in here. I think it'd be so hard to get a non-zero number. Alright, well, you play around with this, x squared. At some point I will get the computer to work out some integrals that, good grief, I didn't think this would be so challenging. Z. So you can see we keep getting these nice symmetric plots. And finally, here we go. We found a density function where in one system you get 16 pi over 3, and then for the other integral you should get the same answer. If you had to do one of these problems by hand, one of these integrals would probably be easier than the other. And I usually think that it's probably this one because of the lack of square roots. Alright, so ends that example of problem number 14.8, 14.7.8 in cylindrical coordinates.